My name's Joanna Sadler. I'm a Chancellor's Fellow at the University of Edinburgh, and my research focuses on valorising waste as a feedstock for chemical production using biotechnology. We have a particular focus on plastic waste. We're very interested in ways to break down plastic and turn it into useful chemicals which might otherwise be derived directly from petrochemicals. To demonstrate the concept of plastic upcycling, we chose to try to convert a waste plastic bottle into the vanilla flavouring called vanillin. So to do this, we engineered E. coli to express a set of enzymes which would convert the degradation product of PET, called terephthalic acid, into the flavour molecule vanillin. So what we did was, having expressed those enzymes in this cell, we added in some pre-degraded plastic bottle into the reaction, and then analysed the products after 24 hours, and were very pleased to see that vanillin had been produced. We then went ahead and did quite a lot of optimization studies on this process to try and maximise the titers of vanillin. So we looked at things like reaction temperature, about the media or the solvent that we were using, and the reaction process conditions as well. And we were able to get almost 1 millimolar of vanillin out of this process. So we're really pleased with that. And this was a really nice proof of concept from which has formed the basis for quite a lot of future work in our lab. Actually done quite rationally. So I started out by looking at the structure of the polyethylene terephthalate polymer, and I thought about, well, if we break that down into its constitutive monomers, ethylene glycol and terephthalic acid, what chemistry could we do on those monomers that could then be useful? And because I have a background in chemistry and biocatalysis, I started thinking about the different enzymes which might act on these molecules, and used my knowledge of these enzymatic transformations to then build this quite rational pathway towards vanillin. So it was done intentionally, but I think what has really alerted to me now is that we can really plug and play a lot of different enzymes now and access a lot of different useful and interesting molecules through a very similar approach, which is really exciting to me. Actually currently produced at about 20,000 tonnes every year, and this is for most famously flavourings and fragrances. So it's in so many different foods. It's in a lot of perfumes, for example, and sort of scent products. But it's also used very extensively in the pharmaceutical industry as a building block for other kind of chemical synthesis. It's used in agrochemicals. It's used as a food preservative. It's used in all sorts of things. So I see the applications being really quite widespread across various different industries. What we are doing now is working with a company to try and optimize and scale up this process to see whether or not it's going to be sort of economically competitive with current technologies. So I think what a lot of people don't realize is that actually most of the vanillin we use at the moment is derived from oil. It's mostly not from the vanilla plant, because that just cannot meet the demand of 20,000 tonnes a year. About 85% is derived from oil. And so what we'd be looking to do is replace some of that 85% with a more sustainable source of this really important molecule. It's found in a lot of different consumer products, most famously plastic bottles. So any kind of drinks bottles, like water bottles or fizzy drink bottles, they're probably made of PET. But it's also used in food packaging, so like biscuit trays or whatever, the food packaging that you see in supermarkets is very often PET. Those are its most famous applications, but actually it's also used extensively in the textiles industry. So anything that is made of polyester fabric is most likely made of PET. So it's spun into fibres which are woven into textiles and used in clothes and all sorts of fabric applications. So it's produced about 30 million tonnes every single year, and out of that about 24 million tonnes is designed to be single use. So the volume of production of this plastic is absolutely huge. And theoretically, if you can break any of that type of PET, no matter what it's been formed into, theoretically, if you convert that back into terephthalic acid and ethylene glycol, then we can upcycle it into vanillin. And what now is happening in the field is really working on plugging that degradation gap in technology. So there's a huge amount of research going into trying to efficiently degrade PET into those two constitutive monomers so that we can then upcycle it. carried out this research as part of a postdoctoral fellowship in Stephen Wallace's lab, and so I was collaborating very heavily with him on that project. I've since become independent, and we are now taking forward this project in collaboration with an industrial partner. So I think it's very important to, when you're working on such an applied project and something which has potential very real-world applications, be working with people who are likely to actually be implementing this technology in the future. So that's why we chose to work with one of the world's main producers of vanillin. We have other projects which are more sort of early stage and proof of concept, and for that we're really interested in working with other academic partners across Scotland who can help to push forward that work. And one example of that is doing some biofilm work with the University of Strathclyde over in Glasgow, where we are looking at the interaction between plastic surfaces and biofilm formation. And that collaboration has proved really useful to really push forwards that research. The vanillin pathway has given us proof of concept that we can upcycle plastic into useful molecules, and I see this very much as just the beginning. So the next step for us is to diversify this into other products. So we are building new pathways to access other industrially important molecules. We are discovering new enzymes which can be integrated into these pathways to expand the scope of this technology. And we're also looking at other plastic types as well. So I see PET as maybe the low-hanging fruit because it's easy to degrade and there are enzymes already known which can upcycle it. The more challenging plastics like polystyrene, polythene, PVC, all these things, these are much more challenging, not only to degrade, but also to upcycle into single products. And that is really a focus of the next kind of few years of our research, is to try and be more ambitious perhaps in what we can tackle and the compounds that we can make.